Hi, this is John Whitaker for the Mathematical Analysis 2 class, and this is our 21st video lecture. And we're still talking about convergence or divergence of series of complex numbers. And we're going to start off today with the P-series test, which has to do with series of real numbers. Here's what it says. So it says, P-series test. Says this series, as n runs from 1 to infinity, of 1 over n to the p, converges if p is greater than 1 and diverges if p is less than or equal to 1. This is a statement that we use quite often in Calculus 2, and so we're going to prove that now. And so, as it's proved, we consider cases. So here's case 1. If p is less than 0, then the limit as n goes to infinity of 1 over n to the p. Now, with p being negative, that really is n to a positive number, and as n goes to infinity, that's going to go to infinity. Okay? And so, or since the limit as n goes to infinity of 1 over n to the p is not 0, then by the divergence theorem, what that tells us is that the series diverges. Then the series is n runs from 1 to infinity of 1 over n to the p diverges. Well, what happens if n is, let's do case 2 here, well, that's where p is equal to 0. And if we take a look at the limit as n goes to infinity of 1 over n to the p, well, p is 0, something to the 0th power is understood to be 1, so we just have 1 a bunch of times, that converges to 1, a constant sequence. And so by the divergence test, theorem, the series is n runs from 1 to infinity of 1 over n to the p diverges. Okay, case 3 will be if p is greater than 0. Okay? And the first thing we're going to do is we're going to consider the sequence 1 over n to the p. We note for that sequence that 1 over 1 to the p is less than or equal to 1 over 2 to the p, which is less than or equal to 1 over 3 to the p, which is less than or equal to, and all of these terms are less than or equal to 0. So this is putting ourselves in that position where we can apply that theorem that's due to Cauchy that we proved at the end of lecture 20. And let me state that. So this sum will converge if and only if the sum, as k runs from 0 to infinity, of 2 to the k, and then it would be 1 over 2 to the k raised to the p power, converges. Now, let us look at that series. The series is k runs from 0 to infinity of 2 to the k, 1 over 2 to the k raised to the p is equal to, well, I can rewrite this as a sum as k runs from 0 to infinity. Here, bringing this to the top, making that to minus p. We get really 2 to the k raised to the 1 minus p. So 2 to the k times 1 minus p is what we can rewrite that. And then we can rewrite this as the sum as k runs from 0 to infinity of 2 to the 1 minus p, all that raised to the k power. And that's the way we'll look at it. Before I leave this, this is a geometric series. It's a constant raised to a number. So, okay, constant raised to the index. And so that's a geometric series. And so we have the geometric series test, and we know that that series, which will converge, so that series will converge, if and only if 2 to the 1 minus p is less than 1. Which occurs if and only if 1 minus p is less than 0. So what that says is that the sum as n runs from 1 to infinity of 1 over n to the p converges when p is greater than 0 if and only if 1 is less than p. And that is essentially our proof, but I'll write a conclusionary statement. So the series as n runs from 1 to infinity of 1 over n to the p diverges if p is less than or equal to 1, and converges if p is greater than 1. So that's the proof of the P-series test. Next thing we're going to do is work on defining the number e. Just spend a little time with it. So as a definition, let's recall this. For an integer n, a positive integer n, for natural number, let's say this, for a natural number, n, we define n factorial, that's written n factorial, by n factorial is equal to n times n minus 1 times n minus 2, all the way down in this multiplication to 1. Multiply by 1. And then it's just a conventional notation so that certain formulas work out. We define 0 factorial to be equal to 1. Okay? So that's what we're going to say. Now here's our definition for E. So the number E is defined to be equal to the sum as n runs from 0 to infinity of 1 over n factorial. That's the number E. Let's make sure that that seems plausible. What do I mean about plausible? Well, to make sure this definition is positive. So we're trying to define a number here through a series. So we better make sure that that series that we're defining that number to be converges. This is sum is n runs from 0 to infinity of 1 over n factorial. We want to make sure that that converges. Okay. So I'm going to look at its partial sum. So let S of n, the term is partial sum, be 1, that's when I have 0, plus 1 over 1 factorial, that's 1, plus 1 over 1 times 2, plus 1 over 1 times 2 times 3, plus, we keep going. Well, let me list a few more terms. 1 over 1 times 2 times 3 times 4, plus 1 over 1 times 2 times 3 times 4 times 5, plus, and we keep going all the way up to 1 over 1 times 2 times 3 times, and we keep going until we get to n. You multiply by n. So that's S of n, determining the partial sum, sequence of partial sums for our series. Now, I want to tell you that that's less than 1 plus 1 plus 1/2 plus 1/2 squared plus 1 over 2 to the third plus all the way up to plus 1 over 2 to the n minus 1. And the reason that's true is because that 2 to the n minus 1 is going to be less than n factorial for n being greater than or equal to 2. So that's what gives us the result that S of n is less than this series of numbers. Okay, so that's equal to, so this addition of numbers is equal to 1 plus, I'll write this down as the sum, as k runs from 0 to n minus 1 of 1/2 raised to the k. And this is going to, so this one match up. This is this series notation, summation notation. This is a geometric series, so here we say this is 1 plus 1 minus 1/2, it's a finite geometric series. 1 minus 1/2 raised to the n, 1 minus 1/2, that's what we get for that finite sum, which is going to be equal to 1 plus 1 minus 1/2 raised to the n over 1/2, which is the same thing as 1 minus, it would be, this part will be 2 minus, and so this is plus here, and this is 2 raised to the, it would be 1/2 to the n minus 1. And 1 plus 2, of course, is 3, and then we take away something, that's 3. So what that tells us that any term in the partial sum is going to be bounded by 3. So since S of n, the sequence of partial sums, is bounded, I'll say this way, is positive, the positive terms, and bounded, then this series, 1 over n factorial n running from 0 to infinity, converges. The reason it converges by that dichotomy theorem, okay, that we proved earlier. This book that we're using gives a theorem, a couple of theorems about E, which I'll just write down. One of them is that the limit as n goes to infinity of 1 plus 1 over n raised to n, that's also E. Sometimes people use this as the definition of E. And another theorem, which we won't prove, is that E is an irrational number. Okay, the next thing we want to do is the root test. And here's what it says. It's called the root test. It says given sum as n runs from 1 to infinity of a sub n, put alpha equal to the limit is n runs to infinity, the lim sup of the quantity nth root of a sub n. Then the root test has 3 parts. 1, if alpha is less than 1, then this series converges. Part B, if alpha is greater than 1, then this series diverges. And finally, part C, if alpha equals to 1, then the series gives no information. I'm sorry. The theorem I'll say the test, this test, gives no information. It's inconclusive. Can't say anything about the convergence or divergence of that series. Okay, all right, let's look at the proof. But before we look at the proof, the root test had to do with limb suits. So let's remember what limb suits are and any fact that we have about it. So this is something that we covered in analysis 1. So let's recall, first of all, this definition. We let S of n be a sequence of real numbers let E be the set of all numbers x in the extended real numbers. And what we mean by the extended real numbers is that they include including infinity or minus infinity, such that, so what x values are we talking about? Such that there exists a subsequence, S of n to k, that converges to x for some subsequence of S of n. Okay. Then, here's the definition. The limb suit, as n goes to infinity, is of S of n equals to the supremum of E. That was the definition of the limb suit. And then we had a fact the following. It had two parts. A, that S star is equals to the limb suit of S of n is an element of this E. And part B says if x is greater than S star, there exists an integer n such that for all n bigger than or equal to big N, that is an F number, that S of n will be less than x. Those two facts that we had about the limb suit. Okay, we're ready now to move on to prove the root test. So here's the proof of the root test. And we're going to break it into cases, and of course because of the conclusion or the statement of the root test. So case 1, if alpha is less than 1. Remember, in this case, we want to show that that series converges. Okay, we can choose a beta so that alpha is less than beta, which is less than 1. There's some gap between alpha and 1, so pick a number in between there. And we're going to use the comparison test here to get convergence. That's where we're headed. So there exists this beta, and by the previous fact, an integer n such that f sub ln of the absolute value of a sub n, so the nth root of the absolute value of a sub n, that is less than beta. And that's for all n bigger than or equal to this big one. And that's true by the fact that we had about the lim suit that I wrote on the other board. So, for all n bigger than or equal to big N, that says that the absolute value of a sub n will be less than b to the n. Now, since 0 is less than b is less than 1, then the sum, or the series, is k runs from 1 to infinity of b raised to the n, or b raised to the k. That converges. And it's a geometric series. Okay. So that's the reason it converges. So, what that says is the sum, as k runs from 1 to infinity, of a sub k converges by the comparison test. So that ends the first part of the root test. Now case 2, that's if alpha is greater than 1, then there exists a subsequence of our sequence. So here I'm going to call that subsequence the n sub k root of the absolute value of a sub n sub k. Okay, since k runs from 1 to infinity, so that's our subsequence. Such that this subsequence, converges to alpha. Okay. And that's true because alpha has got to be in that set E we described earlier to give the definition for the lim suit. By the fact, first part of the fact that I wrote earlier about lim suits. Okay, next, looks very cloudy here. All right, there we get the focus. Since alpha is greater than 1, and the limit as k goes to infinity n sub k root of the absolute value of a sub n sub k is equal to alpha, there exists, well, I'm going to call it k again, but a fancy k. There exists a k, fancy k, which is a real number, natural number, such that for all k bigger than or equal to this fancy k, the nth root of k, the n sub k root of the absolute value of a sub n sub k, that's going to be greater than 1, because it's going to alpha, so eventually it has to be, all the terms of the sequence eventually have to be bigger than 1 to get to alpha, which is bigger than 1. So, for all k bigger than or equal to this script k, this natural number, that would tell us that we're just working through this inequality, that this absolute value has to be greater than 1. Thus, the limit as n goes to infinity of a sub n does not equal to 0. Okay? So by the divergence test, this sum as sum that we're looking at. Oh, well, maybe I'm sorry, I skipped some things. Maybe I should put some more details. I'm getting to the right spot. But, well, this means that the limit of a sub n sub k is different from 0. Okay, that's what you say. No, this was fine. Let's make this change. This is correct. It's going to be different from 0. Okay? What that means is that the limit as n goes to infinity of the absolute value of the a sub n's, well, they can't be equal to 0. And if the norm of the absolute value can't go to 0, thus the limit of the terms of the series itself that we're adding up, they can't go to 0. So thus, the sum as n runs from 1 to infinity of a sub n diverges by the divergence test. Okay. Well, we got one more case to consider here. That last case to consider is when alpha is equal to 1. Okay, and what we're trying to do here, and I'll write this down, is that we want to show that the theorem is inconclusive. So, we want to show that we can't make a conclusion about the convergence of this series of a sub n. And so what we're going to do is look at two examples, two p-series. So first of all, we're going to consider the series as n runs from 1 to infinity of 1 over n, which we know I'll write this down. But 1 over n is 1 over n to the p where p is 1. And we know that's a divergent series. So I'll write that down. So which we know to be a divergent series. Okay. Divergent p-series. Now, since n is greater than or equal to 1, the nth root of 1 over n, okay, is going to be less than or equal to 1. And that's for all natural numbers. Okay. So, any convergent subsets of the nth root of 1 over n, okay, must converge to a number less than or equal to 1. Consider the limit as n goes to infinity of the nth root of 1 over n. Okay? So we want to see what this is. Now, note that the limit as n goes to infinity to handle this, to handle this limit, we really look at the limit of this sequence, ln of the nth root of 1 over n. Okay. And that's equal to the limit as n goes to infinity by using properties of logarithms and rewriting this nth root as 1 over n power. This is 1 over n times ln of 1 over n. Okay. And that can be rewritten as the limit as n goes to infinity of ln of 1 over n over n. Now as n goes to infinity, this part 1 over n goes towards 0. And ln of things that are going towards 0 through positive numbers, they go to minus infinity, and this goes to infinity. Since we've got something going to infinity here in the bottom, we can try to apply L'Hopital's rule, and that's what we're going to do. So using L'Hopital's rule, here I'm using L'Hopital's rule. This is equal to, okay, the limit as n goes to infinity of, so this will be 1 over n, and then I have to take the derivative by the chain rule of 1 over n. That is really minus 1 over n squared, all over, the derivative bottom is 1. So this ends up being the limit as n goes to infinity. This would be a minus 1 over n. That's what I did. And that's equal to 0. Yep, that's what I got. Now, that gives that the limit as n goes to infinity of the problem we want to look at, which is the nth root of 1 over n. that's going to be equal to e raised to the 0. That is e raised to the limit of, let me write it down. It's equal to the limit as n goes to infinity of e raised to the ln of the nth root of 1 over n, which equals e, this part was 0, which equals to 1. Okay. So what that gives us is that the lim sup is going to have to be 1 for this sequence. That's going to be 1. Because every subsequence of this guy, since this converges to 1, every subsequence of this guy has to converge to 1 that converges. So that's an example of where we looked at a series, and this particular part, or if you will, sequence that we looked at, variation that was involved in the series, it goes to 1, but the series diverged. Now we're going to consider another example. Again, a p-series. Consider the sum as n runs from 1 to infinity of 1 over n squared, which we know, what we did today, to be a convergent p-series. Whoops. Okay. Note again that the nth root of 1 over n squared is going to be less than or equal to 1. And that's true for all natural numbers n. Now, I said, okay, look, this has got to be equal to 1. Look, the sequence itself converged to 1, and every subsequence of it had to converge to something less than or equal to 1. So that makes this statement true as well. It's another way of looking at it. And so here, I'll make a similar statement. So any convergent subsequence of the sequence n, the nth root of 1 over n squared, must converge to a number less than or equal to 1. Okay. But we want to make sure that that lim sup is 1. So here, consider the limit as n goes to infinity of the nth root of 1 over n squared. We want to do the same type of work that we did before, and that we'll in considering this limit, we'll also note that the limit as n goes to infinity of ln of this types of terms is equal to the limit as n goes to infinity. Here it would be 1 over n times ln of 1 over n squared, which we can rewrite as the limit as n goes to infinity of ln of 1 over n squared over n. And this is, again, minus infinity over infinity form. So we're going to use L'Hopital rule. So using L'Hopital rule. We get that that's equal to, okay, so I take the derivative of the top, derivative of the bottom, it's limit as n goes to infinity. This would be 1 over n squared, and then this would be minus 2 over n to the third, all over 1, which will be equal to the limit as n goes to infinity of minus 2 over n. And that does converge to 0. So the limit of the sequence we wanted to talk about, the nth root of 1 over n squared, that's equal to the limit as n goes to infinity of e to the ln of the nth root of 1 over n squared, which is equal to e to the 0, which is equal to 1. So when alpha equals to 1, through our work here, we found two examples that we got alpha is equal to 1, but we had two different conclusions about the series. We conclude that we can't make a conclusion. Well, I want to write up the ratio test. And we'll call it quits after that. It's got two parts. So here's the theorem. It's the ratio test. Here's what it says. It says the series summation as n runs from 1 to infinity of a sub n. Okay. Part A converges if the lim sup as n runs to infinity of the absolute value of a sub n plus 1 over a sub n is less than 1, and it diverges if this ratio a sub n plus 1 over a sub n and absolute values is greater than or equal to 1, and that's for all n. Greater than or equal to n sub naught, where n sub naught is some fixed in here. Okay. That seems like enough for today. What we'll do is we'll start up here with the ratio test in terms of it being written, and we'll go into its proof when we start lecture 20. Thank you very much for your time and patience.